Today we're going to be talking about the fundamental theorem of calculus. And you know it's got to be good because it's called the fundamental theorem. All right? But there's really nothing new here. In the last section, we talked about how we could integrate the rate of change of a quantity to get the total change in a quantity. And throughout this whole chapter, we've been looking at ways that we can take information about the derivative of a function and get information about the original function. The fundamental theorem of calculus is the bridge between the derivative and the integral, and it sets the stage for the antiderivative, which we're going to cover in the next chapter. So what the fundamental theorem says is basically the same thing as what we covered in 11.4, but in a little bit more formal way. So if we have a function, a derivative, f prime of t, okay, so this is a rate of change function because it's a derivative, right? And it's a continuous function on an interval from a to b. Then the integral of the f prime function, this derivative function, which is a rate of change function, is the difference between the value of the function, the original function, at b minus the value of the function at a. Okay, so we're integrating a derivative and we get the total change, basically is what it's saying, in the original function. Okay, so just not, like I said, there's not a lot new here. It's kind of the same idea as we covered in the last section, just a little more formally. We're presenting it a little more formally. So let's take a look at example 1. All right, it's a physics problem. So you know it's got to be good. I love physics problems. So here we have a ball that's tossed with an initial upward velocity of 20 meters per second from the roof of a 60-meter tall building. The ball's velocity is shown on the graph. Okay, so we have the graph of velocity, right, which is denoted as d prime, right? So the derivative of the displacement is the velocity, right? So rather than having v of t, we've got d prime of t. Same thing. It's the velocity. So this is the graph of the velocity. And it says fill in the table for the ball's displacement, d of t, and sketch the graph of d of t. And use the frame of reference where d of t is 0 is at ground level and upward direction is positive. All right. So first of all, let's think about just conceptually what's going to happen here. You're tossing a ball upward at 20 meters per second, but you're at the top of a building that's 60 meters tall. Okay, so we're going to assume that we're standing at the edge of this roof, right? And we're tossing it upward, reaching over the edge of the roof, so that when you toss it upward, it's going to continue to fall. It's going to go up, right? And then it's going to eventually, gravity is going to pull it downward toward the ground, and it's going to continue to fall past the level of the roof, and it's going to fall all the way down to the ground. Okay, so you can see that our velocity graph has a constant downward slope, right? It's got a negative slope, which indicates the derivative of velocity is acceleration. So we have a downward acceleration due to the force of gravity, right? So which makes sense. And it looks like it's about 10 meters per second, which is convenient. The actual acceleration of gravity is negative 9.8 meters per second. So this is just the slope of this graph is just indicating reflecting the acceleration of gravity. Okay, now, so you can see at t equals 0, our initial displacement is 60 meters, right? 60 meters because we are standing on top of a 60-meter tall building. Now, what's going to happen? Now you already know what's going to happen, right? We can take we can find the derivative of we can find the area under this velocity curve, and that tells us the distance. And I can do this without the fundamental theorem, right? I know that essentially each of these grid squares represents 10 meters, right? Because it's 1 second by 10 meters per second wide. So each grid square represents 10 meters. Each grid or rectangle, I guess, more of a rectangle, represents 10 meters. So we could just count the area. We could just count up the area. But let's try and use the fundamental theorem of calculus, all right, since we're talking about since that's kind of the theme of today's lecture. All right, so by the fundamental theorem of calculus, right, we're given a distance, we're given a velocity curve, right? And if we know that if we integrate, let's say over the first second, we integrate this velocity, which is a derivative of displacement, with respect to time, we get the difference, right? We get the total change in displacement. So d of 1 minus d of 0. That's what the fundamental theorem is telling us. Okay? So now we know d of 0. So we can actually rearrange this a little bit. All right? And I can actually rewrite this as the d at 1 second is going to be equal to the displacement at 0 plus the integral from 0 to 1 of d prime of t, dt. All right, so and we know d of 0 is 60, and then if I add to it the area under this curve, which is the integral from 0 to 1, then I'll have the displacement at 1 second. All right. So like I said, we can use a trapezoidal rule or use an area of a trapezoid, or we could just say, well, okay, if each one of these is worth 10, then it looks like this is 1 square plus half a square, so this is 15, right? So because we got 1.5 grid rectangles in the area under the curve between 0 and 1, okay? So what we're going to do is add 15 meters to 60, and it looks like after 1 second, the ball is 75 meters. Its displacement is 75 meters with respect to the ground, because we're measuring everything with respect to the ground. Okay. All right. So we can now fill in the table here. We're at 75. And I can also graph it. Might as well graph it while I'm at it. So I'm starting here at 60 at t equals 0. And at 1 second, now I'm at 75. Okay, so there we go. And we could just keep going. We can use the same idea. I know that at 2 seconds, I can take where I'm at 1 second and add to it the integral from 1 to 2, d prime of t. Or I could actually take d of 0 and add the integral from 0 to 2 if I wanted to. Either way, but I already have my displacement at 1 second, so I'm just going to take the 75 meters. That's where I'm at after 1 second, and then add the area under the velocity curve. Okay, and you can see it's half of a grid rectangle, so this represents 5 meters. So I'm just going to add 5 meters, which puts me at 80 meters after 2 seconds. All right, so let's graph that point and fill in the table. All right, so let's now look at what happens at 3 seconds. Okay, now again, I could start with d of 0 and add the integral from 0 to 3, or I could just start at at 2. I could use the distance that or the displacement that I already have, and just add the integral from 2 to 3. Okay, dt. So I'm at 80 meters, and I'm going to add to that. Now notice here, now suddenly we're our area is negative, right? So I can look at the area from 2 to 3, and it's going to be a negative 5. Okay, so now negative 5. So I'm going to subtract 5, add a negative 5. So now I'm back down at 75 meters. All right, so if I want to graph it, it's here, and I'll fill in the table. Right, just keep going in that way. I'm going to run out of room, I think. We'll just keep going. So at 4, I'm just going to take the displacement at 3, which I just calculated, and I'm going to add the integral from 3 to 4 of the velocity curve, of the velocity function. All right, so I'm going to take the 75 meters. That's where I'm at now, and I'm going to add the area from 3 to 4. Okay, so again, I've got 1 grid square and then half a grid square, so but it's below the axis, below the t-axis, so this is a negative 15 meters. Okay, so I'm going to subtract 15. Okay, so that puts me back at 60 meters. Okay, so now it's at roof level again. All right, so I'm going to plot that point and record it in the table. And we'll just keep going. All right, so feel free to pause the video if you're getting tired of seeing the same calculations again, but you can do this on your own. And I'm going to integrate from 4 to 5 now and add it to my displacement at 4. So I'm going to integrate the velocity curve. And so I'm just going to take the 60, and you can see now the area between 4 and 5. It looks like I have negative 10, negative 20, negative 25. Okay, so this whole area is negative 25. All right, so I have to subtract 25 meters from 60 meters, which puts me at 35 meters. Okay, so at 5, I'm going to plot that point and record that displacement in the table. All right, looks like I got one more here. I'll just write it down here. We need to do, find the displacement after 6 seconds. All right, so I'm going to take my displacement at 5 seconds and add the integral from 5 to 6, which is the area under the curve, under the velocity curve. Okay, so I'm at 35, and now let's see what that area is. So I want to find the area from t equals 5 to t equals 6. So 10, 20, 30, 35. What do you know? 35. So 35 minus 35, that puts me at 0. So I'm at ground level here. So my ball has now hit the ground. All right, so let's record that data, and let's connect the dots here. So here's the trajectory of the ball. Now this is over time, but you can kind of see this nice parabolic curve here. Oop. See if I can draw a decent line. All right, that's as good as it's going to get. But you can see that if I could draw a straight line or a nice smooth curve, then you could see that it's a nice parabolic curve, which is what you would expect for a ball, right? So, we toss the ball upward. It goes upward for a while, right? Because it has some momentum going up, but eventually the force of gravity is going to decelerate it enough to stop it and then pull it back down to the ground. So, there you go. Now, again, like I said, here we've taken information about the derivative, and here we've actually graphed the curve of the displacement, right? We were giving information about velocity, and now we have a curve. Now, wouldn't it be nice to actually have a function, have some sort of actual function for that curve? And that's where we're going with this. So, but I've got only one more example, and it's not a physics problem. For you financial people, you'll be glad to know that it's a marginal cost problem. So I will meet you in the next video.